Today, I want to talk about gas mixtures and partial pressures of a gas. Up until now, we've really been focusing on one gas at a time in a vessel, but there's lots of times where we have more than one gas, just like air or something, where it's a mixture of a whole bunch of gases. So the important thing to remember is that in a mixture of gases, as long as they're not reacting with each other, every gas doesn't realize the other ones are there. They act like they're the only gas there, and they each exert a pressure just like they normally would if they were the only gas there. Okay, so then we need a term to define that. Partial pressure just means the pressure that is exerted by a specific gas that's in a mixture. Okay, and then Dalton's law of partial pressures tells us that the total pressure is the sum of all of the individual pressures of the different gases that are in the mixture. So that's kind of interesting. We can take our P equals nRT over V, right? That's just PV equals nRT that is rearranged. And the pressure of gas A is going to be equal to the number of moles of gas A times RT over V. The pressure of gas B is going to be equal to the number of moles of gas B times RT over V. And you can add them all up to get the total pressure. So with a little bit of algebra, you will find out that you could just add up just the number of moles, and this becomes P total, the total pressure, and this is the total number of moles. So you could just add up all the different numbers of moles of gases that you have if you are given, grams of the gases or something, or even moles. And then you can just put them all at once into PV equals nRT and get the total pressure of the system. If you're asked to find the individual pressures, then you have to do them individually, like the number of moles in each one. So, it's not that difficult. Let's look at a couple problems in a minute. Now, we have one more term to define before we can do some problems. This is just called the mole fraction, and it's a little bit like a percent. It's just the ratio of moles. So this is the mole fraction, and it's a Greek letter chi. And it is just the number of moles of gas A over the total number of moles. So if you multiply that by 100, it would be mole percent. But, we just call it the mole fraction, and we use that to find the partial pressure. Now, this is really important. It is the total number of moles. It is not mass. And that is really important to remember, because a lot of times we're given mass, and it is, really tempting to just do mass percent like we're used to. But we need to always convert it to moles and do mole percent. Now, if you were to rearrange these equations up here and do a little bit more algebra, you would find that this is directly related to the pressure. To the pressure of gas A is the same thing as is related to the mole fraction, like directly. So the pressure total. So you can get the mole fraction by either dividing the moles by the total or the pressure by the total, which is really helpful sometimes. All right, so let's do a problem. All right, first problem. A tank contains a mixture. We have oxygen gas, 52.5 grams, and we have carbon dioxide gas, 65.1 grams at 27 degrees C, which we know we have to always convert to Kelvin. So this is, let me move the paper over a little bit. This is 300 Kelvin, exactly. The total pressure in each tank is 9.21 atms. This is total. Calculate the partial pressures of each gas in the container. All right, in order to do this, we need to get the mole fractions. So let's just start out with converting each one of these to moles. 52.5 grams of oxygen times 1 mole of oxygen is 32.00 grams, and we get 1.640 moles of O2. Okay, and let's do carbon dioxide, 65.1 grams of CO2. 1 mole of that is 44.01 grams. And from this, we get 1.479 moles of CO2. All right, so we add these up. We get the total number of moles. We'll just kind of keep it over here. total moles is 3.119 moles. Okay, so that'll be really important in a minute. So now we need the mole fraction of each one of these. So the mole fraction, which is chi, right? So we're going to say chi of O2 equals the number of moles of O2, 1.640 divided by the total moles, 3.119. And we get, for oxygen, 0.5258. And then chi for CO2, we do the same thing, 1.479 divided by 3.119, and we get 0.4742. Now note that they don't have any units. They're just a ratio. So these are moles to moles and they just cancel out. So these mole fractions do not have any units. Okay, so let's go back over to our total pressure, which is here, total pressure. And so we're going to say that the partial pressure of O2 is going to be equal to the mole fraction, which is 0.5258, times the total pressure. So this gives us 4.84 atms. And the partial pressure of CO2 is going to be the mole fraction times the total pressure. And this gives us 4.37 atms. Now, it's really helpful if you just were to add these two things up, 4.84 plus 4.37, and you get 9.21, just to kind of check yourself to make sure that you haven't made any math errors anywhere. Your mole fractions should add up to 1. Your total pressure should be, the sum of your partial pressure. So this should add up to your total pressure. Just kind of a way to check yourself. It turns out that we didn't even need the 300K right here because we kind of did it without that. We didn't have to use PV equals nRT, but I always just kind of convert it just when I'm given Celsius just in case. All right, one more problem we'll do. All right, this is a 100 milliliter sample of air exhaled from the lungs. Okay, so it gives us grams of each of these gases, N2, O2, CO2, and water vapor. It gives us the Celsius. So again, I'm just going to say this is 308K in case I need that later. What is the partial pressure of each component and the total pressure of the sample? So in this case, we're not given the total pressure. So it's not like we can just figure out the mole fraction and multiply it by the total pressure. But what we can do is we can get the moles of each one of these. And there's really two ways to approach this. We can get the moles of each one of these, and then we can use the total moles to calculate total pressure, and then figure out the mole fractions, and figure out the partial pressures of each. But there's another way to approach it too. So let's do this. First, we need to convert each one of these to moles. So 0.0830 grams of N2, and I'm just going to, how to convert grams to moles by now. This gives us 2.963 times 10 to the minus third moles of N2. Okay, and we're going to say O2. This gives us 6.063 times 10 to the minus 4 moles. And then we have CO2. We have 1.454. Did you notice that I'm including more sig figs than I need? Because I've been noticing that a lot of you, this is H2O here because it says water vapor. A lot of you are not continuing to keep enough sig figs in your calculations. You're kind of like sometimes rounding a little too early. So we don't want to round to the proper number of sig figs until the end of the calculation. So right now I want to keep more sig figs than I need in my moles so that when I get to the end, I haven't prematurely rounded. All right, so now that I have moles of each one of these, I can easily figure out the pressures of each one of these, right? Using P of N2 equals number of moles of N2 times RT over V. Okay, so I don't really want to put all of that in there, because it'll just take up so much space on this paper. So we're just going to say the pressure of N2, is 0.749 ATMs. Okay, because I'm using R as the 0.0821 liter atmosphere per mole Kelvin, and I'm getting pressure that way. So the pressure of O2 comes out to be 0.153 ATMs. And again, I'm just putting each one of these moles into the nRT over V. The pressure of CO2 comes out to be 0.0368 ATM. And the pressure of H2O comes out to be 0.0619 ATM. So now I didn't really need to get the mole fraction in order to do those because I just calculated the partial pressure individually. And now from Dalton's law, we can just simply add up all the pressures to get the total pressure, right? And that equals 1.00 ATM in this case. You can add them all up and you just get 1.00 ATM, and that is great. If we had instead added up all of these moles, like I said before, we could have added up all the moles and put it only once into PV equals nRT, and we would have got 1.00 ATM as well. The reason I didn't do that is because the question asks me, what is the partial pressure of each component? So because I needed to figure these out anyway, it's easier just to add them all up since I had already had to do that. But if I was just asked the total pressure of the sample, then I could have just added up the moles and then put it into PV equals nRT just once. All right, one more problem. One liter sample of dry air, 25 degrees C. This is 298 Kelvin. Turns out that I did need that Kelvin in the last one when I put it into PV equals nRT. And we have 768 millimeters of mercury. We have the grams of N2, but we do not know how many grams of the other gases that we have. Other gases including oxygen, argon, and carbon dioxide. So, that's really kind of not a lot of information. So it asks us, what is the partial pressure of N2 in the air sample? And it wants it in millimeters of mercury. So since I'm given millimeters of mercury, I'm going to use the other value of R. If you don't know about the other value of R, I'll just tell you really quick. R can be a multitude of different things. We usually use 0.08206 liter atmosphere per mole Kelvin. But we could also use the same number in terms of millimeters of mercury. So this is also equal to 62.4 liter, not ATM anymore. This is millimeters of mercury per mole Kelvin. I don't know if you can see that on there. Okay, there's my units. 62.4 liters times millimeters of mercury per mole Kelvin. All right, so I'm going to just use this value of R in my PV equals nRT because I don't want to convert to ATMs and then back since it asks me in millimeters of mercury here. So I'm going to say pressure of N2 is equal to number of moles of N2. And if I take this grams and I convert it to moles, I will see that I get 0.03302 moles of N2. And I am not doing that for you because I am assuming that you know how to get from grams to moles by now. So let's put that into our PV equals nRT equation. 0.03302 moles times R, which is 62.4 liters times millimeters of mercury per mole Kelvin. Now I need my Kelvin, which is 298 K. And the whole thing goes over volume, which is 1.00 liters. Okay, so when I calculate this out, let's just make sure that our units cancel. We have our moles canceling here, our liters canceling here, our Kelvin canceling here, and we're left with millimeters of mercury. So I get out of this 614 millimeters of mercury as my pressure for N2. Okay, so that is the partial pressure of N2 in the air sample. That was pretty easy to do. Now it asks me, what is the mole fraction of N2 in the sample? Well, the problem here is that I have the number of moles of nitrogen, but I don't have the number of moles of any of the other gases. So I can't just add up the total moles and divide like I did before. But if you remember, we have our chi, right, of A was equal to not only the number of moles of A over the total number of moles, but also it was directly related to the pressure. So it was related to the pressure of A over the total pressure. So we can do that. So let's just do that. Chi for N2, I should make that a capital N, equals the pressure of N2, which is 614 millimeters of mercury, over the total pressure, which I'm given in the problem, 786 millimeters of mercury. And my mole fraction turns out to be 0.781. Again, no units there. This is like a mole percent, remember? So that would tell us that there's like 78.1% nitrogen in the air sample, which is about right. Well, I hope this has been helpful. If you have any questions, let me know in the comments. And I'll see you soon.